So far, our exploration of information retrieval model has been anchored in the bag of words based approach. We have represented text as vectors in a high dimensional space and calculated similarities using measures like cosine similarity, or we have utilized some statistical similarity measures where the count of the words were used to score a document. In summary, we are considering the term overlap between the document and the query to score the document for that query. So, this term overlaps was considered. However, we have also repeatedly encountered its fundamental limitations. These are models that are blind to meanings. Seeing only the presence or absence of the words is the only thing that these models are considering to score a document. In this lecture, we will discuss how to overcome this limitation. We will discuss latent semantic indexing, or in short LSI, which is a technique that moves us from the surface level syntax of words to the underlying semantics of concepts. The core idea is to use mathematical machinery to discover the hidden thematic structure in a collection of documents. Before we start constructing the structure of LSI, some concepts of linear algebra should be clear to understand LSI. We will be relying heavily on two concepts in particular of linear algebra. First, the rank of a matrix. Intuitively, the rank tells us the number of truly independent directions in our data. If we think of the rows or columns of a matrix as vectors, the rank is the maximum number of rows or columns that are linearly independent. It's a measure of the matrix inherent complexity. Second is the eigenvalue and eigenvectors. An eigenvector of a matrix is a non-zero vector that only gets scaled, not rotated, by the matrix, and the eigenvalue represents the factor by which the eigenvector is scaled. Let's refresh these concepts in a bit detail. Let's formalize the rank of a matrix first. Let's consider we have a matrix called C having dimension m cross n. That is, there are m number of rows and n number of columns in the matrix. Now, we have two concepts called column rank, which is the maximum number of linearly independent column vectors in C, in the matrix C. Similarly, we have another concept called row rank, which is maximum number of linearly independent row vectors in C. Now, an important theorem in linear algebra tells us that the column rank of a matrix will be always be same as the row rank of that matrix. This is why we can simply refer to this as the rank of the matrix, or in this case rank of C, which will be equal to this or this. Now, a key property is that rank of C, matrix C, will be less than or equal to the minimum of the number of either number of row and the number of column. Our data in the form of, let's consider, term document matrix is very often very large but very sparse. Its rank, however, is bounded by the smaller of the number of terms or the number of documents. Now, let's consider a special type of a matrix, a diagonal matrix. This is a square R cross R dimensional matrix where the number of row and number of columns are the same, where the only non-zero entries are in the diagonal. So, if we have a diagonal matrix like this, where number of columns and number of rows are both of them are equal, then diagonal matrix will be having non-zero values only in the diagonal. and rest will be containing 0. Now the rank of a diagonal matrix is simply the number of non-zero entries in its diagonal. Why? Because each non-zero diagonal entry corresponds to a linearly independent vector. For instance, the vector, let's say A 0 0 is independent of another vector which is 0 B A. 0 B 0. So as a result, so if we consider a diagonal matrix as, let's say, A 0 0 0 B 0 and 0 0 C, it is a diagonal matrix. So the rank, as I was telling, the rank of this diagonal matrix will be simply the number of non-zero entries in its diagonal. A specific and vital diagonal matrix is called the identity matrix, where all these diagonal values will be containing the value 1. So in this case, it is called the identity matrix. So in our case, A will be equals to 1, B will also be equals to 1, as well as C. This is called an identity matrix. Now let's discuss eigenvalue and eigenvector. Consider a square matrix now, C having dimension m cross m, that is m is the number of row and m is the number of column as well. Now we are interested in finding a special vector x that satisfy or that have a unique property when transformed using C or transformed by C. If we can find a value lambda which satisfies this equation of the transformation of x by C, we will call that particular value of lambda as the eigenvalue. Let's break this down. On the left of this equation, we have the matrix C, and we have we also have the vector x. That is, basically we are transforming this vector by this matrix C. On the right hand side, what we have is that same vector x simply scaled by this scalar value lambda. So if we can find, so this equation is telling that if we can find a value for lambda that satisfies this equation, it will mean that for a vector x, the transformation by C does not change its direction in the space. So x is remaining x, so it only stretches or shrinks it by a factor of lambda. So transformation of x by this matrix C is only stretching the vector x or shrinking the vector by a factor of lambda. It is not changing the direction. The direction of x is basically an invariant direction of the transformation C, and the scalar lambda is the eigenvalue, and it tells us the magnitude of that stretching. If lambda is negative, the direction is reversed, and the m dimensional vector here, the m dimensional vector that we are getting here is that satisfies this equation for a given value of lambda is called the corresponding eigenvalue. So in this equation, lambda is the eigenvector, lambda is the eigenvalue, and here x is the eigenvector, for this matrix, square matrix C. So how do we actually compute these eigenvalues and eigenvectors from a given matrix, let's say C? Let's say we have a matrix C having dimension m cross m, that is m number of row and m number of column, a square matrix. Now we start from the fundamental equation, this. Now if we extend this equation, it will look like Cx, x transformed by c equals to lambda into x equals to 0. Now we already know that if we have a vector like vector x, if we transform it by an identity matrix, it will be remaining the same. So we will be introducing this here in this equation. So it will be becoming cx minus lambda into x, the vector, multiplied by the identity matrix having the same m dimension. So this is an identity matrix with m dimension. Now if we take this x common, we will be getting this. This is now a homogeneous system of linear equations. We are now looking for a non-zero solution x. A fundamental theorem of linear algebra tells us that a homogeneous system has a non-trivial non-zero solution if and only if the matrix C minus lambda into this identity matrix I is singular. Now what is singular? So a matrix is singular if and only if its determinant is 0. The determinant of the square matrix is 0. Then only it will be considered as singular. Therefore, the critical equation we must solve now is this. This is called the characteristic equation. The left hand side, this is a polynomial of degree m in the variable lambda. This polynomial is called the characteristic polynomial. The m number of roots of this polynomial are the individual m eigenvalues of the matrix C that we have started with. Once we have an eigenvalue lambda, we can substitute it here by substitute it back into the equation here, basically here, and solve to get the corresponding eigenvector. So we will be having eigenvalue, for each eigenvalue we will be having a corresponding eigenvector. Now let's pivot back to information retrieval. This formula represents the cosine similarity score between a query vector and a document vector. The numerator is the dot product, which measures the overlap of term weights, and the denominator here is the product of the L2 norms, that is the lengths of the individual vectors, which serves to normalize the score, making it the cosine of the angle between these two vectors. The crucial point I want to emphasize here is in the item below. So this entire mechanism works based on exact term matching, right? The dot product di qi is non-zero if and only if the same term I is present both in the document as well as in the query. Now this is the core rigidity we aim to break. The model has no mechanism for understanding that car and vehicle are the same concepts or are actually related. There is no notion of understanding that by this model. Now for this query Q, vehicle smoke pollution, document number 1 will be retrieved by those retrieval models, because this vehicle pollution smoke are actually present in the document. So this document will be retrieved. But document 2 is also talking about the same concept, but as these exact terms are not present, it is containing car instead of vehicle, it is containing fossil fuel, it is containing damage of the ecosystem instead of pollution, and so on. So as these query terms are not exactly present in this document, document 2 will never be retrieved by such retrieval models where bag of words based approach is applied. Now let's systematize these problems. First is with synonym. This refers to multiple words having the same or similar meaning. For example, car, vehicle, automobile, and so on. When a document uses synonyms for the query term, our models that we have discussed so far fails to make the connection. The result is a drastic reduction in recall. We miss many relevant documents in this case. Next is polysemy. This is the opposite problem. A single word having multiple meanings. For example, bank for river bank or financial institution bank, or Python for snake or programming language. When a polysemous word appears in a query, the model will retrieve documents containing all sense of the word, many of which definitely will be irrelevant or non-relevant. This severely will be affecting the precision. And the third is the noise. Now, beyond synonymy and polysemy, there is simple noise. Documents might share specific rare words purely by chance without being semantically actually related. Now, Boolean and vector space models are actually susceptible to retrieving those coincidental matches as well. So, these are the problems with this bag of words based model that we have already discussed. Now, let's illustrate this with a concrete numerical example. Here is a small term document incidence matrix. Let's say our query is web surfing. So, the vector of web surfing will be 0, 1, 1, 0, right? This. Now, if we want to score these documents D1, D2, D3 and D4, what we need to do is we need to compute the score, that is, we will be taking the transpose of this into the corresponding document vector. And based on that, if we compute, we will be getting the score, we will be getting the individual score as D1 will be having only 2 term overlap, so it will be 2. D2 will be having 1 overlap. D3 will be having 2 overlap. D4 will be having 3 score because it is surfing is containing twice. D5 will be 1 and D6 will be again 1. This. Now, we see that D4 scores the highest. However, look at D5 and D6. They are about beach surfing. Okay, so their score is low, not web surfing. Still, they are getting some score. Now, they get a score of 1 solely because of the word surfing is present in these two documents. Only because the surfing is present, not the web or not any related terms or any terms related to web. Now, this is polysemy, hurting the precision because these two are actually coming together with this document 2.1 having the same score. Now, let's consider another scenario. The model cannot see that the term internet is related to the term web. The document 2 is containing the term internet surfing, which is related to web surfing. But still, it is getting a score of 1 only due to the fact that only the term surfing is present here. It is not seeing, the bag of words based models are not seeing that internet is actually semantically related to the term web, which was given as the query. This is the problem with these existing models. Now, here is the conceptual leap. What if we had an oracle that tells us that internet and web are related? We could use this knowledge to fix our matrix, right, to put this once. We could, for instance, add small fraction of the internet column to the web column and vice versa. Now, look at the matrix now. I have hypothetically adjusted it with placing a 1 here. If we were to compute the similarity score, the score for D2 and D3 would increase definitely, as you can understand, for the same query web surfing. It is now better reflecting their true relevance to the query web surfing. This is the intuitive goal of LSI, to automatically perform this kind of semantic smoothing. It aims to infer these relationships directly from the patterns of term co-occurrences across the entire document collection. So now we will discuss the formal definition of LSI. Its primary motivation is to overcome the limitation of literal term matching by uncovering the latent or hidden semantic structure. It posits that there is an underlying lower dimensional concept space that generated the observed term document matrix. Now, how does it achieve this? It uses a statistical technique, which we will see is basically called the singular value decomposition or SVD. It projects both terms and documents from the high dimensional term document space into basically a lower dimension called the concept space. So, from term space to concept space. In this new space, the dimensions are concepts or topics. A document about cars and a query about automobile will have very similar query representation in this concept space. I mean, even if their term vectors are not that much having any overlap, still in that concept space they will be close. This is why LSI can in principle retrieve documents with no words in common with the query. So, the mathematical goal of LSI is to find a low rank approximation of the original term document incidence matrix, let us say A. So, why a low rank approximation? Because we believe that the true semantic content of the entire corpus lies in a few strong concepts and the rest of the data is noise or minor variant of those strong concepts. We want to find a matrix A prime from A of a predetermined rank, let us say K, that is as close as possible to this original term document matrix A. Now, the next obvious question is, how do we measure this closeness? How do we understand whether this is A prime is actually close to A or not? Here we use a norm called Frobenius norm. For a matrix X, the Frobenius norm is defined as this. It is the analog of the Euclidean distance for vectors. So, we are finding rank K matrix A prime having rank K that minimizes basically this Frobenius norm difference. This A prime is our denoised, semantically smoothed representation of the entire matrix. So, our target or the target of this LSI is to find this matrix. Then how to approximate the matrix? The solution to this low rank approximation problem is provided by a powerful theorem called singular value decomposition, or in short SVD. The theorem states that any m cross n matrix A of rank K can be factored into three matrices U, S and V. Here U is will be an m cross R matrix with this ut dot u, that is the transpose of u dot u definitely will be an identity matrix of dimension R. S is an R cross R diagonal matrix. Its diagonal entries, that is all the entries in the diagonal, are singular values, and by convention they are sorted in decreasing order. And finally V is an R cross n matrix. Its columns will be called the right singular vectors. The columns of this will be called the left singular vector, and the columns of this will be called as the right singular vectors. They are also orthogonal, meaning that V into V transpose will be identity matrix. Now this diagram actually visualizes the entire SVD. It shows how an original M cross N matrix A is decomposed into the product of one M cross K matrix, another K cross K matrix. Here I was referring to this as R, here it is K, and one K cross N matrix. So the singular values are crucial. They indicate the energy or importance of each corresponding latent concepts. The first singular value corresponds to the strongest concept in the corpus. The second to it is the next strongest, and so on. Basically these. Now we use SVD to solve our low rank approximation problem, to approximate a low rank approximation of this A, that is A prime having rank K. To get this, to do this, we will be using truncated SVD. So from this, considering this with the SVD of A, what we will be doing is we will be considering UK, which is the first K columns of this U matrix, that is this. Then SK. SK will be the upper K cross K submatrix of this S. Remember, these are containing the topmost K singular values, the most important K singular values, and then VK be the first K rows of this V matrix, which will be a K cross N matrix considering this K rows. Now, the Eckert-Young-Mirsky theorem tells us that the matrix AK equals to this UK, the approximation that we have done, the truncation that we have done, UK into SK into VK is the closest rank K matrix of matrix to A, then the closest approximation having a rank K in terms of the Frobenius norm. This process is like a lossy compression. We are keeping the K most important concepts and discarding the rest. So this is essentially kind of a lossy compression. So we know, given a matrix A, SVD gives us one approximation of A having rank K, which is in the low dimension. So this is our conceptual approximation. But how do we actually compute it? The key lies in a related decomposition for a specific type of a matrix, which is called eigenvalue decomposition, or in short EVD. EVD works on real symmetric and square matrices. So for a real symmetric square matrix, let's say B, something special happens. It's guaranteed to have a full set of eigenvectors that are not just independent but orthogonal and normalized as well. We can pack these unit eigenvectors into a matrix U, which has the property, of course, U into U transpose or U transpose into U equals to the identity matrix I. This allows us to decompose B into this. It's a perfect factorization of this B into rotation, scaling as well as reverse rotation. But our term document matrix that we have started with A isn't square or symmetric. So how does this help? How does this EVD, eigenvalue decomposition, helps here? The trick is to look at the A transpose or A transpose A, which are both symmetric as well as square. A transpose will be M cross M matrix, basically term cross term matrix. Its eigenvectors from the these are the eigenvectors from the columns of our U matrix earlier, and A transpose A is an N cross N matrix, that is document cross document matrix, number of document cross number of documents. Its eigenvectors form the columns of our V matrix. So by the law of this eigenvalue and eigenvectors, there will be orthogonal matrices U and V, and there will be diagonal matrices S1 and S2 satisfying this. Now let singular value decomposition exist for a matrix A, that is this equation is there, holds. Then A dot A transpose will be this, extending that will be observing that V transpose identity. So we can write considering S and S transpose as S square. So A transpose will be U A square U transpose. Similarly, A transpose A will be V transpose A square V. So here the columns of U matrix is in the SVD are actually the eigenvectors of A transpose. The rows of the V matrix are the eigenvectors of A transpose A, and the singular values in the S matrix are the square roots of the eigenvalues from either of these products. So SVD is fundamentally an extension of EVD to rectangular matrices. Now how do we operationalize this for retrieval? Here we will be discussing three different ways of doing that. First option is very straightforward. Instead of using the entire term document incidence matrix, use the approximated one. As a result, the score of all the documents will be the transpose of the query into this approximated term incidence matrix. Now our ultimate target is to score all the documents in the collection, right? After applying this, the score will be one matrix and we will be considering those values having the highest scores from this matrix. So here there is a problem. The problem is immediate and actually severe. AK is dense, unlike A, which was very sparse. So it is actually an M cross N matrix where M cross N most of the entries in the M cross N in this matrix AK will be having non-zero values. So for any realistic corpus M, the number of terms, and N, the number of documents, will be huge. Storing this again dense matrix will be computationally infeasible. Further, computing the score Q transpose into AK is of complexity order of M cross N, which is kind of expensive. Now the second option is much smarter. Instead of using AK or even A, we will be using VK. VK represent each document's coordinate in the new k-dimensional concept space. Now we also map the query into the same space. Now the similarity score is just a dot product in this concept space. This is incredibly efficient, as we can understand. From order of n cross m, we are now ending up with order of n cross k. K is much less than m. The third option offers another perspective. We can think of Tk as a linear transformation, a semantic filter that we apply to the original matrix A. In practice, we can even binarize this Tk to create a kind of automated thesaurus that adds related terms. While still we are at the dense matrix space, this view allows for potential optimization like sparsifying Tk by thresholding small entries, effectively creating an automated thesaurus for query expansion. Now in practice, LSI is rarely used in isolation. Why? Because while it excels at improving recall by finding conceptual matches, it can sometimes harm precision. It might retrieve documents that are conceptually related in a broad sense but not directly relevant to the specific information need of the user. Therefore, the most robust approach is to use a hybrid scoring function. We take simply a linear combination like this of the original term matching together with the LSI conceptual term matching. The final score here is this, where this alpha is the linear interpolation parameter, the tuning parameter between which will be considered in between 0, so it should not be, it's alpha, and it will be in between 0 and 1. This gives us the best of both the worlds. We maintain the precision of exact query, exact keyword match of this by this, which are often very strong signals, while still leveraging the power of LSI to boost the ranking of relevant documents that would have been missed by literal model alone. So we are incorporating the semantic similarity here by this LSI score.